Hi, welcome to the classes with Nadia. In today's class, we can discuss preformulation studies. These are done on a new drug molecule if it shows sufficient pharmacologic effect in animal model to permit evaluation in man. These studies are focused on the physicochemical properties of that specific compound which would affect the performance of drug and development of an efficacious dosage form. This preformulation studies gives confirmation regarding the drug's eligibility or compound's eligibility to develop a new dosage form. Once a pharmacologically active molecule has been identified, the first step is to optimize the molecule for further developments. Commonly, modifications which brings changes in stability and or solubility of the molecule is the optimization process for that compound. Salts, prodrugs, solvates, polymorphs, or even new drug analog may be the outcome of these modifications effort. Among this, salt and prodrug approaches are most common. Salt formation improves solubility of the compound, thus bioavailability possibly. But salt formation is limited to molecules with ionizable group. Prodrugs may be formed with any organic molecule having a chemically reactive functional group. Prodrugs are compounds with intrinsic pharmacologic property but must undergo some transformations in vivo to liberate the active drug molecule. After optimizing the molecule form of drug, formulation development commences. Objective of preformulation studies is the quantitation of those physical chemical properties that will help in developing a stable, safe and effective formulation with maximum bioavailability. The following is the outline of the principal areas of preformulation research. We can categorize it into three: bulk characterization, solubility analysis, and stability analysis. In this video, we are going to discuss about bulk characterization, and this includes the examination of shape, size, flow properties, morphology, etc. of a raw material or say a particular compound to develop into a formulation. Bulk characterization is done on small particles individually. This studies comes under micromeritics. Micromeritics is the study of particles having micron size. It's a vast area of study actually. Let's check some of these important profiles of a compound under bulk characterization. And the first one is crystallinity and polymorphism. To characterize a solid form, one have to verify that the solid is the expected chemical compound, identify the internal structure, and describe the habit of the crystal. Okay, then what's habit and internal structure of a molecule? Outer appearance of a crystal is described as habit, while the molecular arrangement within the solid is called as internal structure. Internal structure of a molecule can be crystalline form or amorphous form. Crystalline form is a very systematically arranged group of continuous constituent atoms or molecules in a three-dimensional space, whereas the random arrangement of constituent atoms or molecules in space, as in a liquid, is called as amorphous form. And this amorphous form is prepared by rapid precipitation, lyophilization, or a rapid cooling of a liquid melts. Amorphous forms have higher solubility and dissolution rates than crystalline forms owing to their higher thermodynamic energy. Due to the same reason, they are unstable too. And this thermal instability can occur during bulk processing or within dosage forms, so is the major disadvantage for amorphous form to develop into a dosage form. Coming back to crystalline form, it's of two types. They are single entity polymorphs or molecular adducts like non-stoichiometric inclusion compounds and stoichiometric solvates. Non-stoichiometric adduct contains entrapped solvent molecule within the crystal lattice. This type of adduct are avoided for development due to its lack of reproducibility. On the other hand, stoichiometric adducts contain crystallizing solvent into specific sites with the crystal lattice. within the crystal lattice. They are usually referred as solvates, and if the crystallizing solvent is water, they are called hydrates. Hydrates have less solubility than their anhydrous form. So, conversion of an anhydrous compound to a hydrate within the dosage form may reduce the dissolution rate and extent of drug absorption. The other category of crystalline form is polymorphs. It is the ability of a compound to crystallize as more than one distinct crystalline species with different internal lattices. This difference in internal lattice brings many physico-chemical stability and solubility changes to the same compound or element. Melting point, vapor pressure, density, hardness, crystal shape, etc. are some examples where polymorphs vary each other. Polymorphs are of two types, enantiotropes and monotropes. Sulfur is an example for an anisotropic polymer because it can change from one crystalline form to another by varying temperature or pressure. Glyceryl stearate is an example for monotropic polymorph because it's unstable at all temperatures and pressures. During preformulation, it is important to identify the polymorph that is stable at room temperature and to determine whether polymorphic transitions are possible within the temperature range used for stability studies and during processing. Next one is fine particle characterization. Particle size, shape, and surface morphology directly affects bulk flow, formulation homogeneity, dissolution, and chemical reactivity of compounds. Let me explain some methods or techniques which are used to characterize some particle properties. First method is using a light microscope with a calibrated grid which usually provides adequate shape and size characterization for particles. Particle size in the range of 0.2 to 100 micrometer can be measured by this method. Sampling and preparation of the microscopic slide must be performed carefully to obtain a representative dispersion. Light microscopy is time consuming, but it has only few restrictions on particle shape. Another method is conductivity method or stream counting devices. This technique provides a convenient method for characterizing the size distribution of a compound. Samples for analysis are prepared by dispersing it in a conducting electrolyte like sodium chloride. A non-volume of this suspension is then drawn into a tube through a small aperture across which a voltage is applied. As each particle passes through the hole, it is counted and sized according to the resistance generated by displacing that particle's volume of conducting medium. Okay, then the counter provides a histogram output within the limits of that particular aperture tube. Other stream counters are based on the principles of light blockade or laser light scattering for sizing each particle. We can conclude as a fluid suspension of particles passes through a sensing zone in which individual particles are electronically sized, counted and tabulated. It is the working principle of a stream scanning system. The system has some disadvantages too. Some are non-spherical particles are not sized accurately. Needle-shaped crystals have a tendency to block the aperture hole, and it is unsuitable for polar and highly water-soluble materials due to solvation instead of dispersion. And other methods for particle size analysis are sieve method and image analysis. Okay. Now we can move on to another property, surface area, which is more directly related to processes like dissolution and degradation than particle size. Surface area can be estimated using appropriate geometric equations and through direct measurements. Direct method involves adsorption method and air permeability method. Direct methods are used to measure specific surface area of porous materials. A more precise measurement of surface area is made by nitrogen adsorption or wet nitrogen adsorption. The method is like a layer of nitrogen molecule is adsorbed to the sample surface at minus 196 degrees Celsius. When this adsorption reached equilibrium, the sample is heated to room temperature, then nitrogen gets dissolved. Its volume is measured and converted to a number of adsorbed molecules via ideal gas law. Now we can calculate the surface area per gram for each pre-weighed sample, as we know each nitrogen molecule occupies an area of 16 A square. Then coming to surface morphology, it can be observed by scanning electron microscopy. This method serves to confirm qualitatively a physical observation related to surface area. Most of the modern SEM instruments also provide energy dispersive X-ray spectroscopy analysis of surface metal ions, which may prove beneficial in interpreting an instability or incompatibility problem. And another property is bulk density. This is of very great importance when we consider the size of a high dose capsule or the homogeneity of low dose formulation, in which there are large differences in drug and excipient densities. Bulk density depends on particle size distribution, shape, and cohesiveness of particles. Based on bulk density, powders can be classified as light and heavy, light and heavy. Light powders have low bulk density and heavy powders have high bulk density. Bulk density can be calculated as mass of a powder divided by bulk volume. It is determined using mechanical taper apparatus. Non-mass of drug or formulation is placed in the graduated cylinder of this apparatus. Then it is tapped to obtain a minimum volume for this powder bed. Using the weight of the powder in cylinder and the minimum volume, we can calculate bulk density. For the computation of void volume or porosity of packed powder bed, it is desirable to know the true density of it. True density equals weight of powder divided by true volume of powder. Experimental methods to find true density is gas displacement and liquid displacement method. Then we can discuss powder flow properties. Pharmaceutical powders are classified as free-flowing or cohesive powders. Many of the flow properties are significantly affected by variations in particle size, density, shape, electrostatic charge, and adsorbed moisture, which may arise from processing or formulation. Thus, a free-flowing drug candidate may become cohesive during development and demands a complete new formulation strategy. The intention of preformulation powder flow investigation is to assess the pharmaceutical consequences of each process improvement and provide direction for the formulation development. And all these properties we have discussed are coming under bulk characterization of a compound. These are some of the important bulk characterization properties. So we can discuss the solubility properties in the next class. Thanks for watching. Bye.